Hello everyone. In this session, we are see about ambiguous grammar and ambiguity in context-free grammar. Introduction to ambiguous grammar. A grammar is said to be ambiguous if there exists more than one leftmost derivation or more than one rightmost derivation or more than one parse tree for a given input string. If the grammar is not ambiguous, then we call it unambiguous grammar.
In this lecture, we will be studying about ambiguous grammar. So what do we mean by ambiguous grammar? A grammar is said to be ambiguous if there exist two or more derivation tree for a string omega. That means two or more left derivation trees. Okay, so in the last lecture we have studied about derivation trees and we saw how we can draw derivation trees for the strings of a certain grammar. So let's say that we have a grammar given and there is a string omega that can be generated from this grammar. And if this string omega can be derived from two or more left derivation trees, then that grammar is said to be ambiguous. So when we mean two or more derivation trees, we should keep in mind that they should be both left derivation trees. It's not that you form one using a left derivation tree and another using a right derivation tree and that is ambiguous. No, that is not the case. It is only when it can be formed using two or more left derivation trees, then it is said to be an ambiguous grammar. Okay, so now let's take a simple example to understand this in a better way. So here we have an example. We have a grammar G which is given like this. It has S as a non-terminal symbol or the variable, and it has terminal symbols A plus B plus and this multiplication sign, and we have P as the production rule and S is the start symbol. And the production rule is given like this: S gives S plus S, and S can also give S into S, and it can also give A, and it can also give B. Now we want to generate the string A plus A into B. This is a string we want to generate, and let's see in how many ways we can generate this string. Okay, so let us start with the start symbol, which is S, and I will say that S gives S plus S. I will start from this production. S gives S plus S. Okay, now I need to get A plus A into B. Now this A is what I need to get, and I am forming the left derivation tree for this. So this is a left derivation tree, so we have to start from the leftmost symbol, which is S. So here this S, I will replace it with A because we have a production which says S gives A. So this S will be replaced by an A, and the other S, let me just write it down as it is. And now I got this A plus S, and now this A, let me write it down as it is, plus, and I have another S over here, and I need A into B. Now for that, let me further expand this S using the production rule which says that S gives S into S. So this S will be expanded as S into S. And now I will replace this S by A because we saw that S gives A and I need A in my string. So this A I'll write down as it is, and this S I will replace it with A and into S as it is. And now this final S I will replace it with B. Now I can do that because the production rule says S can give B. So this A will be as it is, this A will be as it is, into this S will be replaced by B. Okay, so now I am getting the string A plus A into B, which is a string I wanted to generate. Okay, so this is one way I can generate this string. Now let's see another way in which we can generate. I will again start with the start symbol, and now I will start with the production which says S gives S into S. This one, S into S. Okay, so this is again a left derivation, so we should start with the leftmost symbol. So here this S over here I will replace it with S plus S. S gives S plus S, so this S I will replace it with S plus S, and this into S I write it down as it is. Okay, so this is what we are getting. Now why am I doing this? This is because I want to get this string. and we see that there is a plus symbol in between and we were having into. So if I do this, I can get the symbol plus. Now I'm having s plus s into s. Now this s over here, I will replace it with a because s can give a. So a plus and this s into s. Let me just write them as they are. And now this s over here, let me replace it with a again. A plus a into s. And then this final s, I will replace it with b because s can give b. So a plus a into b. So now I am getting my string a plus a into b, which is the string I wanted to generate. So we see that this string a plus a into b were generated using two derivation trees. First I chose the production rule s plus s and I could get the string, and even when I chose the string s into s, I could get this string. And we have seen that in both the cases we use the left derivation tree. So using the left derivation tree, we were able to derive the string in two ways. Thus we can say that this grammar is ambiguous. Alright, so this is the example of an ambiguous grammar, and I hope it was clear to you. So thank you for watching and see you in the next one.
Next, let us see about ambiguity in context-free grammar.
In this session, we will discuss about the ambiguity in the CFGs. So without any further ado, let's get to learning. Coming to the outcome of this session, today we will acquire the understanding of ambiguity in context-free grammars with the help of an illustration. Now, if you all remember, in the previous session, with the help of this grammar, we wanted to derive this string of terminals. We also observed that using the leftmost, rightmost, and parse tree derivation, we finally achieved our intended string. Let's now observe if there is any other way to derive the same string using these procedures. Let's begin with the leftmost derivation method. Now the last time from the start symbol e, we derived e plus e using the rule e can be rewritten as e plus e. This time, let's use the next rule, that is, e can be rewritten as e into e. So from e, we derive the sentential form e into e. Now this is leftmost derivation procedure, so we will be concerned about the leftmost variable, which in this case is this one. Now observe the string. We have acquired the multiplication operator and now we need the addition operator, right? So this time we will use this production, that is, e can be written as e plus e. So expanding the leftmost e, our derivation becomes e plus e into e, and now we have achieved the format. From all these, this is the leftmost non-terminal. And now we will simply derive id from this because the format is already achieved. Now from these two, this is the leftmost one, so we will derive id again. Now we are left with only one e. Let's expand this one. So we now have derived the string id plus id into id. Well, this is the intended string. So observe, although we started off with different production rules, by the end, we ended up achieving the same result. So there are more than one leftmost derivations for this particular string. Let's now observe whether that's also the case for rightmost derivation. So here also we will start off with the second rule, so e derives e into e. Now remember, this one is the rightmost derivation, and from these two, this is the rightmost one. If we notice the string after the multiplication operator, we have id. So expanding this e, we will derive the sentential form e into id. Now there's only one non-terminal, so let's expand that. Notice that we have covered the last portion and we are yet to derive this portion. So from this e, using the first rule, we will derive the sentential form e plus e into id. Now there are two e's and among them, this is the rightmost one. Since we have achieved the format already, using the third rule, that is, e can be rewritten as id, we will derive the sentential form e plus id into id. So we are almost there. Now all we have to do is expand the only e. So finally, we will derive id plus id into id. And this is the intended string. So similar to the leftmost derivation, there are more than one rightmost derivations for the same string. Let's see if that's also the case for the parse tree derivation. So we will start off with the start symbol e. Now unlike the last one, this time let's derive e into e from this. Now from this e, we will derive e plus e. And finally, from all these e's, we will derive ids. So if we traverse the tree, top to bottom and left to right, the yield would be id plus id into id. So yes, there are more than one parse tree for the same string. Now remember this, for any grammar, if we obtain either more than one leftmost derivations, or more than one rightmost derivations, or more than one parse tree, then the grammar is clearly ambiguous. If it had been unambiguous, the derivations should have been unique and one and only. Due to ambiguity, all the parsers except operator precedence parser will get confused and will produce wrong outcomes. We will observe that in upcoming sessions. Now, ambiguity is actually an undecidable problem. If you want more insight about it, you can refer to the post-correspondence problem, which has been beautifully explained in our Theory of Computation course. So the question remains how to fathom whether a grammar is ambiguous. Well, there is no concrete approach to that. However, we will learn to solve this in the next couple of sessions. Anyway, do always remember that for any grammar, if there remains more than one leftmost derivations, or more than one rightmost derivations, or more than one parse tree, then the grammar is ambiguous. So in this session, we understood the concept of ambiguity in context-free grammars.